They're going to be able to tell the difference between whether something is true or false. We're going to be doing that within the context of just the world in general and math. So you guys need to be aware of that. So what we're going to do is we're going to look at these 5 examples and we're going to determine if they are true or false, right? True means that both the beginning half and the second half are true together. They work together. They kind of flow through. Can you open the door, please? All right, that's when it's true. Both the beginning and the end, the hypothesis and the conclusion are true. An example of being false, right, to show a statement is false, in the sentence right here, you need to think of only one example where the hypothesis is true, but the conclusion is false. That means that you know the first half is true, but you can think of something that proves that the second half is false. That's called a counterexample. So if you think something's false, you have to prove it to me. You can't just say, oh, that's wrong. You gotta tell me why, right? So let's take a look at the first sentence. It says, if 2 angles are vertical, they're congruent to each other. Is that a true statement? Yes, that's the definition of vertical. All right, so we know that one's going to be true. I wrote true, you guys can circle the T. All right, so that's a true statement based on our understanding of vertical angles. All right, this next one, it says, if 2 angles are congruent to each other, they are vertical. Is that a true statement? If 2 angles are congruent to each other, then they are vertical. That's true or false? It is false. I gave it away with this extra little box here. All right, but why? Why is that false? Could you explain that to me?
Not all vertical angles. You know.
No.
Or not all angles be vertical.
Okay, so everybody hear what Jameson said? She said, not all angles have to be vertical in order to be congruent. Can't you have just 2 random angles that are congruent but not vertical?
Yeah.
Vertical angles have to create that V shape. Well, can't do it with me. Like this. They create a V shape where the 2 angles right there are congruent. You can just have 2 like random angles that aren't even touching that are congruent. So the way that we know this is false is you can have 2 angles that are congruent but not vertical. Do you guys see how I did that? I said this is true. I have 2 angles that are congruent, but those 2 angles are not vertical. So counterexample, there are angles that are congruent but not vertical.
We have to write counterexample.
No. I just expect that if you say false, whatever you're going to write next is the counterexample, right? So in writing a counterexample, you would say, okay, I know that there are angles that are congruent but not vertical. First half is true, second half is false. If you'd like to draw a picture, that would also be helpful. And I'm not going to try to draw on the board because that tends to mess it up. So if you guys were to draw a picture of 2 angles that are congruent but not vertical, how would you draw that?
A line going the face and the other line right underneath it going across.
You draw something like this maybe? Are those angles congruent?
Yeah.
Are they vertical?
Oh, no.
No, right? I have 2 angles that are congruent but not vertical. That's an example, a visual example of that counterexample. So if you want to write it in words and draw a little picture, that might be helpful. The visual can usually be really helpful in understanding why this is false. Okay? All right, what about number 3? If a shape is a triangle, it has 3 sides. That's true. You guys all know what a triangle is, right? It's a shape with 3 sides. That's the definition. So for that one, that's obviously a true statement. Right? If it's true, you don't have to prove that it's true to me. It's only when it's false that you have to prove it's false. All right? If it's not raining, then there are no clouds in the sky. Okay, who can explain a counterexample for that? Why is that false?
There are clouds. It could be like that weird.
Be careful how I need you guys to word it very specifically. The way that you word a counterexample is very specific. Remember, a counterexample is when the hypothesis is true, but the conclusion is false. So the way that you word a counterexample is by saying, it's not raining, but there are clouds in the sky. Right? So you could say, counterexample, it could not be raining, but there are clouds. Right? It's called an overcast day. And it's really, really cloudy, but it's not raining. That's how you word a counterexample. You have to say the first part, it's not raining, however, there are clouds in the sky. That's a counterexample. Keep the first half true, and then the second half would be false. You don't have to write it as a conditional, because see, I didn't really write it as conditional there. But you have to say, okay, the first half is true. It's not raining, right? But there could be clouds in the sky. The opposite of the second half could be true. The opposite, right? So that's how you write a counterexample. Right, what about if it's cold, then it's snowing? Is that always true? No, right? What's the counterexample?
It could be cold and not snowing.
Yeah, it could be cold, but not snowing. That's your counterexample. It could be cold, but not snowing.
I'm not sure what this.
Okay, again, like I've said before, counterexample is when the first half is true. You just say the hypothesis is true. It is cold. But to give me a counterexample, you have to think, is it possible for the second half to be false? Is it possible to be cold and not snowing? Yes. So that's why the original statement was not true, because it was trying to say that if it's cold, it has to be snowing, which is not true. Well, this is logic. It's logic, which is a sort of math, but that doesn't relate to numbers. All right, so counterexamples are really, really important. So you guys need to be able to know if a statement is true or false and be able to prove that to me. Okay, this is one of the skills we need to be practicing in this particular lesson. All right, moving on from that, though, I want to talk about things that are logically equivalent. You guys know what equivalent means? Yeah, equal, right, mean the same thing. So logically equivalent statements are statements that always have the same truth value. So if one statement's true, the logically equivalent statement is also true. If it's false, then the logically equivalent statement is also false. Okay, so they're both true or both false. That's logically equivalent. So if you guys remember, we learned some types of statements last time, the inverse, converse, contrapositive. Remember this? We can have a relationship between these statements in order to find out equivalence, right? So let's say we started with the conditional statement. The conditional is just your starting point, your if P then Q. You just have a random statement, okay? The statement that is logically equivalent to the original statement is the contrapositive. The conditional and the contrapositive are logically equivalent. So think about this. I'm going to give you guys a true statement. Right? Logically equivalent means they have to have the same truth value. So I'm going to give you a true conditional statement. If the sun is up, then it is daytime. This is true. That's a definition of day. The sun is up. Set it down, right? Okay. So if the sun is up, then it is daytime. That is a true statement. What if I said, if it's not daytime, then the sun is not up? Isn't that also true? If it's not daytime, that means it's night. And if it's night, that means the sun is not up. Do you see how when you flip the statement and add not, they both are true? That's logically equivalent. If it's not daytime, then the sun is not up. That is also true if the original statement is true. Okay? This is very important. So this line right here, put a little star. This one's not as important. The second one is not as important, but the first one is very important. The conditional and the contrapositive are always logically equivalent, and we use that idea a lot. So you guys need to be okay with that. If you have a statement, if you reverse it and write the opposite of both the beginning and the ending, it's going to be true. All right. What are the other two statements we learned? What are they called? Do you remember? Okay. So the converse and inverse are also logically equivalent. Converse and inverse are also logically equivalent. Right, so the conditional and contrapositive are going to be the same truth value, and the converse and inverse are going to be the same truth value. This little statement right here is also important for us. They could all have the same truth value as well, right? If the conditional is true, the contrapositive is true. If the converse is false, then the inverse is false. But they could also all be true at the same time. Okay, so that's something that you want to be looking out for, which we're going to look at the next page. But they could all be opposite, like these two are the same, these two are the same, or they could all be the same. So just keep that in mind. All right, we're going to practice that idea right here in this little section right here. Okay, I have 4 statements. One of them is blank, so you guys are going to help me find that out. I'm going to write down all the 4 statements, the original, inverse, converse, and contrapositive, and then I'm going to draw lines to match which ones are equivalent logically. Okay? So this top left corner is always the conditional. So if the sun is out, then it's daytime. That's the original idea I was telling you guys about. Right? Oops. What do I call this statement? What's the name? This is the inverse. Then you guys write that at the top. Inverse. This is the inverse. Let's actually label all of them. So this is the conditional. This one in the upper left-hand corner is the conditional. And this one in the upper right-hand corner is the inverse. So we're going to label those. Okay. So conditional inverse, what would I call this one? This is the converse, right? It just took the two ideas and swapped them. So we're going to label this as the converse. And make sure everybody can follow along, please. All right, so I have the conditional, the inverse, and the converse written. What's the one that I don't have? The contrapositive. So I need you guys to write down the contrapositive in this box. You guys got to know what the contrapositive is. You're going to write the contrapositive of the conditional, and we'll start with that one.
Is this kind of the question you're going to say in this kind of box?
No. So just our setup for now. Anybody know what the contrapositive would be for the statement? Austin?
It's not daytime and the sun is not out.
Okay, so if it's not daytime and the sun is not out or isn't, you can use contractions as well. Alright, so now I have the conditional, the inverse, converse, and contrapositive all written. I need you guys to draw lines to connect which ones are logically equivalent. If this is the conditional, which one is the same truth value as this one? The contrapositive. So I'm going to draw a line between these two. These two are logically equivalent. The conditional and the contrapositive. So draw a line connecting those. Right? Then I have the inverse here. What statement is the inverse logically equivalent to? The converse. So you're going to draw a line connecting these two. Right? So you need to be able to identify what type of statement they are. So the inverse, converse, contrapositive, or the original, and then know which one's equivalent to which. All right, next example. If you are healthy, then you keep good habits. This is our conditional, so label that. This is the conditional statement. This is how it starts. What would I call this statement? This one started as, if you are healthy, then you keep good habits. This one says, if you keep bad habits, then you are not healthy. That's the contrapositive. They reversed the ideas and wrote the opposite. That's called the contrapositive. So let's label this one as the contrapositive. Right? And then what would this one be? If you are not healthy, then you keep bad habits. What would that one be? This is the inverse. So label that as the inverse. Same order, but opposite. It's called the inverse. So what's the statement that I don't have written? Converse. The converse. So I need you guys in this empty spot, you need to write down the converse of the conditional statement.
You said this one like here is contrapositive?
No, this is the upper left-hand corner of all these is conditional. This one is the conditional.
I think the converse one is kind of smart to say, then you'll be healthier than you are.
Alright, so what's the converse of this original statement? Yeah.
If you keep good habits, then you are healthy.
Yes. That's the converse. If you keep good habits, then you are healthy. Or you will be healthy, or whatever. I don't care what tense. Alright, so go ahead and label this converse as well. So we have the converse. Now, what would I draw a line between? We said this one was the conditional. Which one is equivalent to this one? The contrapositive, which is where? Right across from it. So you're going to draw a line between these two. These are logically equivalent, the conditional and the contrapositive. Then we have our converse, one you just wrote. What's that logically equivalent to? Inverse, which is right next to it. So you're going to draw a line between those two. Alright, does that make sense? Alright, the last one's a little bit demented, but sorry. I'm going to have you guys do that one on your own. Again, you're going to label. This one is always the conditional, the upper left-hand corner. This is where we start. This is the conditional. I want you to label the other two that we have, write the one that's missing, and then link the ones that are equivalent to each other. All right, so try to do that one on your own. Label each statement, found the one that's missing, and then link them together. All right, how do you label this one? This is the, no, this is the conditional, always starts as a conditional. What's this one? This one right here is the contrapositive. This one, and then the one we didn't have was the converse, which is, I don't know. I don't even know where that example came from, but whatever. All right, how would you link them to equivalence? The conditional is equivalent to what? Okay, so you link these two, and then the inverse is equivalent to the converse, so you link those two. All right? Questions on that? Yes.
I was just wondering, how do you know like which is the P and which is the Q?
So
like,
I'm telling you right now that the upper left-hand corner is a conditional, but in another question they would tell you like the conditional statement is this, and P is always first and Q is always second in the conditional statement, and you just compare everything to that conditional statement. Okay. They'll be more specific in actual questions. All right, if you turn the page, this is our last idea that we're going to talk about today. It's a new vocabulary word called biconditional. And you guys, what are some other words that have the word, or well, what does bi mean when you add that to the front? It means two. So when we're talking about a biconditional statement, that means two conditional statements, all right? This is a really interesting idea. The biconditional statement combines two conditional statements into one sentence. It takes two ideas and combines them. The two ideas that it's combining is P arrow Q and Q arrow P. This is called the conditional, and this is called the converse. They're taking the conditional and the converse and merging them together. The only way that this can happen is when both of those statements are true. If the conditional and the converse are true, you can merge them together to create a biconditional. Okay, so both have to be true, right? If you're going to put them in one statement, I want you guys to circle this right here. This is new notation, right? See that little double arrow? They took the two arrows and they kind of merged them together, so it goes both ways. It goes from P to Q and from Q to P. So the little double arrow stands for biconditional. Okay? The way that you say this out loud is P if and only if Q. So it's the word if and only if. That's what the little double arrow stands for. And as is true mathematician's way, feel free to abbreviate it with IFF. You can do that when we're writing it down. Yes. You don't have to physically write out if and only if, you can abbreviate to IFF. Okay? If. Yes. So again, and I highlighted this, I don't know if it printed on your guys' notes because it's black and white, but a biconditional statement can only be written if the converse is true. This is very, very important, right? So what you're going to do is read the statement, determine if the statement is true, write the converse, decide if the converse is true. Guys, listen. If both of those statements are true, then you can write the biconditional. I'm going to show you how. All right, so take a look at this example. Determine whether to write the biconditional or give a counterexample. If your converse is false, that means you can't write a biconditional, but you have to prove to me why it's false. Okay, just like we were practicing on the first page. So here's our conditional statement. If an angle's measure is below 90 degrees, it is an acute angle.
True.
Is that true? That's the definition of acute, right? What would the converse be of that statement? Oscar?
If it's an acute angle, then it's below 90 degrees.
Okay. I don't want you guys to use pronouns in the hypothesis, so don't use it. Say if the measure of an angle, if an angle is acute, right, so the converse has this first, so if an angle is acute, then its measure is below 90 degrees. I mean, I won't take points off, it's just confusing for me to understand what you're referring to. So don't have the it in the hypothesis. All right, so if an angle is acute, then its measure is below 90 degrees. That's the converse. Everybody agree? Oh, let me finish writing. Converse, if an angle is acute, then its measure is below 90 degrees. Is that a true or a false statement?
True.
It is true, right? It's still the definition of acute. It still works out, right? So the original was true. The converse is true. Can we write a biconditional? Yes, we can, right? And this is how you do it, right? A biconditional does not have the word then. Regular conditional statements go if, blah, 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 then, blah, 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 right? The way that we write a biconditional looks like this. You have P, there's no if at the front, you have P, an angle's measure, is below 90 degrees, then you have your if and only, I left out the if, sorry, if and only if, it's acute. That is supposed to be it. I just said the idea. Remember how the first idea is P? So you have your hypothesis first, if and only if, and then your conclusion. I wonder if it'll let me change that because it's a typo. No, well, I don't think so later. Sorry. That is right here that I'm covering with my cursor supposed to be an if. Sorry. Just write it down, then we'll go over it again.
I'm trying to figure how it.
I'll explain it in a second. Just write it down. Alright, once you guys finish writing it, the way that we're going to break this down. If and only if is saying that one thing is only true if the other thing is also true. Right? An angle's measure is below 90 degrees. The only way that can happen is if it's acute, correct? That's why we write it as if and only if. The only way that you can have an angle's degree measured less than 90 is if it's acute. That's why we use if and only if. It's another way of saying that it's kind of guaranteed both ways. Right, and again, you can use IFF instead of writing out if and only if. Feel free to do that. But that's how you write a biconditional. I will take points off if you write an if at the beginning or if you use a then, because that's not how you create the structure for a biconditional. You have P, your hypothesis, the double arrow, which is if and only if, and then Q, your conclusion. So make sure you write it correctly. I'll show you another example so you guys can see it again. Okay? So take a look. Well, if you'll let me scroll. Shit, might not. Take a look at the second. Take a look at the second example. It says determine whether to write the biconditional or counterexample of, or at the end, sorry. Your conditional statement says if you can draw a line through points, then they are collinear. Is that a true statement? Let me illustrate with a picture. If you can draw a line, oops, well, if you can draw a line through points, does that make them collinear? Yes, right? They're on the same line, the line that you just drew, right? So that statement's true. What would the converse be? Take a second to write it down. Write the converse of if you can draw a line through points, then they are collinear. Alright, anybody want to share what the converse is? Okay.
If it's collinear, that you can draw a line through points.
Does that make sense grammatically?
No, not logically, no.
No. Let's try a little bit of an edit with the wording. Yes? No, sorry. Yeah, there we go. Yes, very good. That's a lot better grammatically. If points are collinear, then you can draw a line through them. Takes the two ideas and swaps them around. All right, so let's think about whether this is true or not. All right, if points are collinear, look at the picture I drew. Are these collinear points? Okay, then you can draw a line through them. So they started out as collinear. Does that mean that I can draw a line through them? Yeah. So is that true still? Yeah. So the original and the converse are both true. When that happens, can you write a biconditional? Yes, you can. Does anybody know how you would write it? What would the grammatical structure be for this biconditional? Would you start with the word if? No, not for a biconditional. How would I start it? You, okay. Keep going.
You can draw a line through points.
Yes, you can draw a line through points. Then what comes next? If and only if, then
They're
yes. You can draw a line through points if and only if they are collinear. You have the first idea first, if and only if in the middle, and then the second idea last. And again, feel free to use IFF as an abbreviation. Alright, so everybody see how we did that? The trick about this, like, once you guys write the converse, you guys know how to do that. We've been doing that since last class. Writing the biconditional, you'll get the hang of that too, writing that structure. What's tricky about this is knowing whether the converse is true or false. That takes a deep understanding of math, these concepts, right? You may not have understood it unless you drew a picture, right? So sometimes that's what makes this a little bit more complicated is you have to really think about your understanding of math to know if that's even true or not. So make sure you're aware that that's going to be something to take into account. All right, the next thing is pretty straightforward. I'm going to do the reverse, right? And those examples, we had the conditional and the converse and then wrote the biconditional. For this one, I give you the biconditional. I want to know what the conditional and converse are. So here's the biconditional. It says, lines are perpendicular if and only if they form right angles. What would the conditional statement be? Yes. All right, what idea should come first in the conditional? The beginning one. So if lines are perpendicular, the conditional and the biconditional have the same order of ideas. So if lines are perpendicular, how would I finish it? Then they form right angles. It's the biconditional, the same order, but instead of if and only if, we put the if then back. I'm doing the reverse of what we just did up there. So if your biconditional says lines are perpendicular if and only if they form right angles, your conditional would be if lines are perpendicular, then they form right angles. Okay? What would the converse be? If lines form right angles, then they are perpendicular. So two same ideas, but you swap their order. So that's the definition of a converse. So take a second to write that.
Actually, plus not as tired. What plus is it?
5.
Plus is it?
Plus. Oh, isn't this plus?
Earlier in second grade, right now. It's plus 5.
I gotta go house.
Anywho, guys, does that first example make sense?
Yeah.
You take the biconditional and break it down. Yes? What about example 2? A shape is a triangle if and only if it has 3 sides.
If a shape is a triangle,
Okay, if a shape is a triangle,
then it has
then it has 3 sides. You take the same structure as the biconditional, but you change it to an if-then instead of if and only if. Same order, different kind of setup.
Is there a way to put it has into one?
Nope, there's no contraction for it has. Sorry. Now that we know the conditional, what would the converse be? Yep, if a shape has 3 sides, then it is a triangle. Okay, so
It's not really math. It's just like
it's logic, yeah.
I like the logic.
Alright, so is everybody okay with both directions? Kind of starting with the conditional converse and then writing the biconditional and going the other way too? Everybody okay with that? Alright, I feel like the trickiest part of this lesson, and I am reaffirmed by Oscar, is finding counterexamples. Okay, so this last section here is just finding counterexamples. We're just going to practice that. Okay, so all of the things that I've written here are false. All these statements are all wrong. But you guys you have to tell me why. And you have to write a counterexample properly and include a visual to help you. Okay? So this first statement says, if a polygon has 4 sides, then it is a square. Okay? This is false. Can you guys explain to me why?
There's polygons do not have 4 sides.
No. Henry?
Because,
That's orthogonal sides.
because
Hold on.
I'm pretty sure it can't a polygon be, isn't it like no definite shape?
No.
Just a
You
polygon.
guys are going way too broad with how you're approaching this.
It's because there's multiple polygons on 4 sides.
Yes, there we go. You guys are going way out into polygons with a different number of sides. No. Remember, you have to say that this is true. For a counterexample, the first half has to be true. So you guys were thinking to things have 8 sides. That's not this.
It's not.
Right? You have to think of a polygon that does have 4 sides, but is not a square.
Like a trapezoid.
Like a trapezoid or a rectangle or a diamond or just some weird wonky shape that has 4 sides, it's not a square. That's how you have to think of a counterexample. The first half is true. You have a polygon with 4 sides, but the opposite of the second half. It's not a square. An example would be a rectangle or a kite or whatever you guys want to draw.
I just spelled square wrong.
Okay. You've all heard that.
It's a circle.
No, please don't draw a circle. It's not a polygon. Nor does it have 4
No,
sides.
I'm just saying, like, my uncle, he kept hearing me say, like, it's not a circle, it's a square. Sometimes, like, as they say a statement, you're going to say something else and say, it's a circle, not a square.
Alright, cool, sorry. Alright, the next one over here. The next one over here says, if 2 angles share a common side, then they're adjacent. This one's a little bit more of a brain teaser. It is false. So can anybody tell me why? Remember, for a counterexample, you need the first half to be true, and then the second half to not be. Can you think of an example in your head where two angles do have a common side, but they are not adjacent? Can you picture that?
No.
Oh, you think of
They share the side.
A straight angle,
And then other lines.
like that. What's the shared side? Here, look, I'll label it. A, B, C, D. I want to know where you're going with this. What's the shared side?
A, B, C, share, C.
So these two? So you're saying this angle and this angle, they share the side? All right, but they're adjacent still. That's not a counterexample. That is an actual example. That's not a counterexample. That's an example of it being true. And which can happen. You can have part of it true, but if you can think of one example where it's false, that makes the entire statement false.
Wait, is there have to start with
No, that's just how that's how I word my counterexample. All right, I'm just going to show you guys because this one can be really, really abstract. Okay, what I just drew right here. I can also show it on the board because I probably put it a little bit better. What I just drew, right? See the black angle and the blue angle, right? Don't they both have this side right here in common? This one right here on the left. They both have that side. Then you have the really big angle, the black one, and then you have the blue one, which is the smaller one. Why they are sharing a side? Why are they not adjacent?
because it doesn't share. The
blue one
does
doesn't
not share.
No, that's not how adjacent angles work.
I am confused. Wait, is it like the long way around? Like the
Yeah. So one angle is like this. It's the full angle. Yeah, let me draw them separate. I don't know the Pac-Man reference.
Okay, like if you like make a circle and the part that's the angle is like out, and it's like the like you draw a circle. Wait,
So look, I have two separate angles.
it's like that.
No. Guys, I have two separate angles, the black one and the blue one. The reason why they're not adjacent is because they're inside of each other. Adjacent means next to, right? So they'd have to be sharing a side, but on opposite sides. They're sharing a side, but this one's inside of that one. Adjacent can't be overlapping. This angle, I moved it and stuck it inside of another one. If they're inside of each other, that defies the definition of adjacent. So you can have two angles that are sharing a side, but if they're overlapping, that makes them not adjacent. Alright, so that's a little bit of a brain teaser. You guys might have not as easily known that was false.
So how is that one inside count?
The blue one, see if I could take the blue one out, blue is part of the black one. You can't have them overlap. That's not the definition.
What if those lines weren't drawn? Like what if the
They would have to, they would draw them.
What if they weren't drawn?
If they weren't drawn and you're talking about this angle and this angle, those two are adjacent.
Okay.
But when they're overlapping, they're not. Okay, so that one's a little bit tricky. You guys probably won't see one quite that abstract, but just in case. Alright, what about this one? If two angles are adjacent, then they form a linear pair. Is that always true? Do two angles that are touching always have to be a linear pair? No. So the way that you would word the counterexample is, two angles are adjacent, but they're not a linear pair. Two angles are adjacent, but they're not a linear pair. First part's true, second part's not. So I just drew you an example. Your stereotypical adjacent angles. They're next to each other, but they don't create a line. And there's another illustration of the difference between adjacent, where they're just next to each other but not overlapping, and the previous one where they are overlapping. And you can draw any example you want. Any two adjacent angles that don't create a line, there are a bunch of them out there. Okay? Then our last one here says, if a number is divisible by 2, then it is also divisible by 4. Is that always true? Okay, so what's a counterexample? Okay, if a number is divisible by 2,
But we
Then
can't
it
use it.
can be divisible by 2.
no, you want the opposite of the second half. It is divisible by 2, but
Not
not divisible by 4. What are some examples of those numbers? 18, 6, 10, 14, 22, etc. There are numbers that are divisible by 2 and divisible by 4, like 4, 8, 20. But if you can think of examples where it's not true, that's why this is false. For it to be true, it always has to be true. If you can think of at least one example where it's false, it makes the entire thing fall apart. Right? So this is how we come up with counterexamples. Again, the first part is true, and then you have to think, can the second half be false? And if so, give me an example. All right? That's our lesson. So, what I want you guys to do for me really quick, with your phone, if you have a little QR scanner thingy, I think it's embedded in the Snapchat or something. Scan it, and it's going to take you to a Google form. Listen.